So I want to tell you about symmetries of Feynman integrals, which is a name for a new method for computing Feynman diagrams. And this is work I've been doing with my professor, with my advisor, Professor Barak Kol, and with Philip Burda at the Hebrew University of Jerusalem. So first of all, let me remind you what is a Feynman integral in case you haven't calculated one recently. So if you have a Feynman diagram which has loops in it, you take the product of propagators and integrate over the loop momenta, where the momentum flowing in each propagator is some linear combination of internal momentum and external momentum. And of course, the value of the integral should depend only on the parameters, which are the masses of the particles taking part in the diagram and Lorentz invariance of external momentum of particles coming in. Let me denote this set of parameters by x, and we shall call this, you'll see why later, we'll call this the parameter space of the diagram. So as physicists, we always look for symmetries, and one obvious symmetry of the Feynman integral is performing linear transformations in the space of loop momentum. Now, to get useful equations from these symmetries, let's consider an infinitesimal transformation where we transform the momentum flowing in loop A by a little bit of the momentum flowing in loop B. And this, of course, should not affect the value of the integral, since this is merely a change of integration variables. But nevertheless, it gives us useful equations, as written, the delta I equals 0. And acting with this operation and the integrand, we get 4 types of terms. The first type are constants, which could depend on the space-time dimension, times the original, times our integral. Second kind of terms, we have a squared propagator in the denominator, and we interpret this as a derivative by the corresponding mass. In still other terms, one propagator could get eliminated and another one can be squared. We call these degenerate diagrams and also source diagrams, and you will soon see why. We could also get numerators over a squared propagator, where by numerator I mean terms which I cannot resolve in terms of propagators which appear in the denominator. And we don't want these terms. To get rid of them, let's refine our definition of the symmetry group and define the space of squared propagator momentum. And let's restrict ourselves to the following group of transformations. These will be all linear transformations which preserve this space of squared propagator momentum. In this way, each generator of the group will give us a partial differential equation in parameter space. And you see the structure has these constants times the integral. We have differential operators, and we have, as sources, linear combinations of degenerate diagrams. Note in particular these differential operators. This set of differential operators defines G orbits in our parameter space. And the main idea of this method is that within a G orbit, we could reach any point from any other point through a line integral, and the smaller the codimension of the G orbits, the larger the region we could reach in parameter space. In the next 2 minutes, let me tell you about 2 results to illustrate the ideas I told you about. So consider the following 3-loop Feynman integral. It has 3 mass scales, because the 2 bottom propagators are massless. The parameter space in this case is 3-dimensional, and using the procedure I described above, we could find the equation system. And if you look good at the differential operators which appear here, you see they are linearly independent at a generic point in parameter space. This tells us that the codimension of the G orbits is 0, and therefore the G orbits fill all of parameter space. From here, we continue in the usual fashion. We find the homogeneous solution. We could find the full solution by variation of parameters, from which we could find the gradient of this function C in terms of functions of the degenerate diagrams. And now we could find the value of our Feynman integral at any point B by taking a line integral from some point A through some path gamma, by integrating over this gradient. And all we need to know is this gradient, which comes in terms of generate simpler diagrams, and the value of the integral at some point A, where we usually choose it to be a point where we could calculate the value of the diagram easily. For example, here we chose A such that all masses are 0 besides the mass x1. Thank you very much.
One question for Ruth. Okay, let us thank Ruth again.